In this lab session, the instructions to create a crane model to determine the equivalent K for a crane model will be explained, and here is shown the statement for the problem. So this is the statement for the problem that will be used to make understand the methodology and the schematic for the crane model has been shown here. So this is the schematic for the crane model where a boom has been attached at point A and a cable starting from point F and passing through this pulley, and it wraps around this movable pulley DE, and a weight W has been suspended. So our requirement will be to determine the vertical oscillations of this suspended load under initial excitation. So first of all, we will be creating the model for this crane model. So to create the geometry, we will be starting model module, and from the start we can input its density to be very small, for example 10 is power minus 40, so that this boom and the cables are to be massless, and only the effect of this weight W suspended is accounted for. So now we will be starting geometry module, and once it has been loaded, then the method to create geometry for this crane model will be explained. As the design model has been loaded, we will be creating the model in XY plane. We will be clicking on XY plane, and then we can click on sketch, look at face plane or sketch icon, or we can click here on the Z-axis so that planar view is shown, and go to sketching tab, and now we can create the necessary geometry for this crane model at any location, but it is better that we can specify some origin point to start. So for this purpose, the origin start midway between point F and A. Here at this location means at a distance 1.5 meter from both point A and point F. Remember that this distance need not be necessary to be equal. So here in the diagram, it is shown equal the distance. So we can start from line command, and here start from the origin, and when point constraint P is shown, we will be starting from here, and we will be drawing a random line, and after that we can set its dimension here, linear dimension, and we can input here the distance is 1.5 meter, and then we can zoom fit it, and after that we can use move command from the dimension so that a better view is shown, and furthermore we can control zone like this, and after that we can draw the next line segment and make it here. And here, as it is shown that both of these segments about this vertical line are of same length, so we can use equal constant, or we can independently dimension this line segment. So if we can use constraint, then we will be using equal length constant and making this line to be equal to this line, and in this way this total distance between point A and F has been decided. And remember that it is not necessary to draw these two lines, because they are actually this distance between point F and A is grounded. So we can remove these lines later on. So after that we will be starting this cable portion FC. So we can draw it at some random angle here like this, and from the input data and the calculations we can observe here that this theta, it has been calculated to be 35.0736, and this length L1, which is the cable length, here it is shown cable length, this is 12.3055, 3055. So we can input these values. So first of all, if we can dimension it here like this, then this value of length must be 12.0355. So 3055, sorry. So 3055 here like this, and later on the angle between this line and this line, here we can use alternate angle. Again we can use alternate angle like this, and this angle as it has been calculated here to be 35.0736. So inputting this angle here, that 35.0736, 0736. So in this way its dimension has been set, and now we can simply delete these two lines, because they were only required to set point F here at this location. So this distance could have been specified using horizontal dimension like this as well. Here, as we can observe that this distance is 1.5 meter. So here we can observe that the cable has been specified. And now it is very important that we will not be creating this boom portion in this sketch because the cross-sectional area for the boom and the cable are different. So we have created cable in sketch 1, then we will be creating this boom portion in another sketch as individual sketch so that different bodies could be created. So we have created the cable. So go to sketching tab here and convert it into lines from sketches. So make it a line body and here we can generate it. And after that we will be specifying its cross section, and the cross section for this cable, its cross sectional area for the cable, it is shown here 100 millimeter square. So we can calculate its radius. So as the cross section, as the cable is circular, so its area will be pi r square. So we can say that r square will be equal to 100 divided by pi. So we can divide it by pi and this comes out to be 31.830. And now this is equal to r square. So we will be taking its square root and this comes out to be 5.6418 millimeter. So we can convert it into meter divided by 1000 meter. So 1000. So this comes out to be 0.005648. So the radius is 0.00564 can be rounded off. So here we can go to concept and create cross section and circular, and here we can assign 0.00564 and 2 meter. So the cross section has been specified. Now we assign the cross section by selecting it here like this. So circular one, it has been assigned, and here we can visualize the cross section solids. And here if we zoom window this portion, and as we can observe that the cross section has been specified like this. And after that we will be creating the model for after that we will be creating the model for this boom portion. So what we will be doing, we will be clicking on XY plane, and then we will be clicking on here at new sketch. So sketch 2 has been added. So click on sketch 2, highlight it, and then go to sketching tab and click on line, and here click on Z-axis to put it in planar view, and then we can make it off cross-section solids temporarily, and here we can create the next line segment here like this point is common, and again we set the dimension between this point and this line to be 1.5, and furthermore we can set the angle between this vertical line and this boom is 45 degrees. So we can set the angle, we can select this line and this axis, for example, and then we can click here on alternate angle like this, and this angle is to be 45 degree. Here by default it is shown, so we can make it confirm 45 degree. So angle 45 degree has been set out in this way, and now we will be going to a modeling tab, and we will be selecting sketch 2, and here we will be converting it into a line body. Here we will be applying, and here it is very important that we will be making it add frozen, not add material. If we make it add material, then both the cable and this boom will be converted into single body. So as these both bodies have different cross sections, so we will be making one of them to be as add frozen. So add frozen property has been applied. So click on generate, and here like this. After that, we will be defining the cross section for this boom, and here we can observe that the cross section for this boom portion is length is 10 meter, and its cross-section area is 2500 millimeter squared. So here, first of all, we must confirm that the length for this must also be 10 meter, and it has been confirmed. So after that, we will be adding the cross section. So click on concept, go to cross section, and here its cross section is also circular. So to calculate the radius for this area, what we will be doing, that this cross sectional area is equal to pi r square, means the radius of for the boom squared. So dividing 2500 divided by pi, this comes out to be 795.7747. So this is equal to radius squared. So we will be taking its square root, and this comes out to be 28.2094 millimeter. So we can divide it by 1000 to convert it into meters. So this comes out to be 0.0282094. So we will be assuming the radius to be 0.02821. So we can round it off as, so here the radius is 0.02821. So after that, we will be assigning this cross-section circular 2 to this line body, and now we can show with the help of cross-section solids. And here in the 3D, after making all the sketch planes off, this is the final model which has been created. We can look it in a zoomed manner. So this is the cable and this is the boom portion has been created. So geometry has been created like this. And here we can uh, also confirm if uh, its properties, but here it is not shown because it is a line body. We will be observing them in analysis module. So we will be now starting this model cell A4. So design model cell has been activated. So in this way, this model has been shown here. And now we can click on and check its properties here. And we can observe that this line body 1, it has a length of 12.306. So this was actually the cable, and we can observe here its cross-sectional area, which is shown here. And similarly, this line body, it has also shown here. So we can observe here that its cross-sectional area is same as we are given in the statement. So after that, a very important point here is that we will be creating a connection between these 2 points, between this cable and the boom portion. So the connection between these 2 points is actually a fixed joint. So we can create a joint here like a fixed joint. So we can, for example, first height this cable and then we can click on this joint, and here in the reference, for example, we can select this point and we can click on apply, and after that we can show this line body and we can make this boom as the hidden body, and again go to this fixed joint, and now click on this mobile here and click at the same point and click on apply, and as a fixed joint has been applied. So after that we will be creating analysis settings. So its mode must be 1, as this is a 1D problem. And after that we will applying necessary constraints here, and we can apply a displacement constraint here at point F, and again we can show here at wireframe mode. So here at this location, and it is very important to note here that at point F and point A, it is better that we will be creating two pin connections. So to create pin connections at point F and at point A, we will be using one displacement support with all X, Y, and Z coordinates to be 0, and one fixed rotation constraint. So one fixed rotation constant with rotation in XY plane to be 0, and rotation about Z axis must be free. So what we can do, that in the displacement we can click on this point here we have applied, and here it must be 0, it must also be 0, and here it must also be 0, and so we can rename it here that this is displacement at F. So after that we can apply a fixed rotation constant at the same point F2, so that it is created a pin joint. So we can make Z rotation free, rotation about X and Y must be fixed. So rotation above fixed rotation, it has been made free, and after that we can apply a similar constant here at this location. So we can, for example, duplicate these constraints and we can rename them. We can click here and then click here, so that this first selection has been deactivated, and now click on at this point and then click on apply, and the same, and here we can rename it to be that sorry, we can rename here that this is the displacement at point A, and we can similarly duplicate this fixed rotation. So this fixed rotation is also at point F. At point A. So it's fixed rotation. So we will be selecting the same point here, and similarly this fixed rotation was at F. So two pin joints have been applied, and after that we will be applying one further displacement support at this location so that it has been confined to move along vertical line. So this must be 0x, and z must also be 0, and y must be free because it is confined here to move along the vertical orientation, as it has been stated here that the spring constant is in the vertical direction. So in which direction the spring constant is required, so in that direction we will be making the displacement to be free. After that, the important point is to create this weight W. So the weight W for can be assumed, for example, we can say it 1000 Newton. So we can calculate the corresponding inertia or mass in kilogram for the weight. So if the weight is 1000 Newton, then its mass will be 1000 divided by 9.81. So this comes out to be 101.936. So we will be applying a point mass at this location. We will be clicking on geometry, insert, and create a point mass. And then we will be clicking on this common point, and we will be inputting the mass 101.9368 kilogram. So mass has also been applied, and after that we will be, so this is the displacement. We can say, we can rename it at W. So at load point or W location. So after that we will be inserting a deformation total, deformation to, and simulate it, solve it, and let us see if the solution is performed successfully or if some error occurs. So here we can observe that the frequency comes out to be 79.36. So our next task is to verify this frequency. Here, first of all, we can show its simulation like this. Now our next task is to confirm this frequency or verify this frequency. So what we will be doing, that we will be creating a simple mass spring system having the equivalent stiffness of this value and the mass which was corresponding to weight of 1000 Newton, and to create that mass, that verification, so we can launch a parallel module here, and here we will first of all be creating a unit mass. We will be creating a mass of given value. So we can click on XY plane here and go to Z axis to put it in sketch view. And then here we can, for example, create a simple volume, and here we can make a symmetry axis and click on this point and click on this point, so that, and after that we will be creating a new symmetry axis, this horizontal axis, and then click at this location and at this location, so that it is has been made symmetric. And after that, furthermore, we can create an exact cube. For example, it has an equal length. So, and after that, we will be setting its dimension. So, to create the mass, we will be determining that the weight was 1000 Newton and its mass came out to be 101.9368 kilogram. So to specify this mass, we can assume the volume for this cube to be unit. For example, we can assume that the volume for this cube is unit meter cube. So 1 meter cube, if the volume of this mass is, then as we observe that the density is mass per unit volume, then it means the density will be same as equal to the mass. So what we can do here, that we can dimension this to be 1 meter, for example, here like this. So we have created a unit volume rectangle, and after that we will be clicking on sketching tab here and highlighting the sketch one and clicking on here extrude, and here we will be applying the direction vector, means the direction must be both symmetric, and here it must be 0.5, so that the total extrusion is 1 meter. So the cube has been created. So here we can observe its properties, that this is a solid of 1 meter volume, 1 meter cube. So in this way, it has been created, and after that, we will be going on its engineering data, and here we can input its density to be unit, so that the same mass has been satisfied, and after that we will be launching its model cell. Before and once it has been loaded, then as the model has been imported, and here we can calculate its properties. Its properties can be verified that this is a 1 meter, the mass is 1 kilogram, and after that we will be analysis setting what its mode must be 1, and after that we will be applying the spring, and we will be clicking on model cell full insert and go to connections, and in the right click on connection insert and go to spring and click at this face, and remember we will be putting the stiffness here. Longitudinal stiffness is this value 26.4304 and is power 6 Newton per meter. So input the same stiffness so that it has been verified. So here must be, we can simply copy from here 26.4304 and we can paste it here and E6. So this has been 10 raised power 6. So after that the connection must be body dash ground, and in the mobile tab we will be clicking on scope and here at this location and click on apply, and we can observe its coordinate as coordinate is 0.5, and so we can go into the reference, and if we are required the length to be 1 meter for example, then here we will be inputting 1.5 because 0.5 is the distance from the origin. So in this way a spring has been successfully applied. So after that we will be confining the movement for this cube. So we will be clicking here on model and apply a remote displacement at, for example, this face, and we will be confining its movement only in x direction. For example, y must be 0 and z must also be 0, and in this must also be 0, and this must also be 0, and rotation must also be 0, and its behavior here must be rigid. So after that we will be inserting deformation and total deformation, and here sorry here we have made some mistake here because the mass here is 1 kilogram, but this mass must be, as the mass was calculated 101 point, mass was calculated 101.9368. So to input this mass here, we will be going on this engineering data here, and we will be inputting now the same density because the volume is unit. So we will be inputting 101.9368. So this must be the density, and after that we will be refreshing the materials and then we will be checking the properties of the solid so that the same mass has been shown here. And now we will be solving it and checking if the frequency has been verified or not. So here, as we can observe, here the frequency was 79.63 hertz, and here the frequency is 81.04. So it is approximately equal and the error is very small. So it has been verified. We have had created the same mesh as it was in the model, and after that we had applied the same stiffness as it was required here. So the frequency has been verified. Thanks for listening and your patience. Assalamu alaikum.